constitutional rights. So here's an architectural drawing of the, using our system. So first off, the sender reveals to the receiver the relevant firearm information and their member authorship authorization proof to the receiver. And the receiver receives that, verifies the physical serial number on the device, on the asset, and the app in the background validates the sender's authorization. If the receiver then agrees to this exchange, they will generate a received confirmation proof. And once that's complete, they'll reveal that to the sender. The sender will then confirm that transfer and also confirm or verify the proofs from the receiver. And then once that's all complete, it will broadcast all 4 proofs to the network, which will move the ownership from the sender to the receiver. I guess I'm missing a slide. So we need to show 3 things overall. So the first proof is that we need to show that both the sender and receiver are members of the network, and then they have the correct status to exchange the firearm. There are many different types and classifications of firearms in the United States. There's different qualifications necessary to own them. There are also accessories that modify the classifications of specific firearms, and this is all dependent on varying state and federal laws, which makes it a really, really complex thing to determine the status of a particular firearm. We want to ensure that the minimum possible status is met in order to conduct the exchange. So this is kind of communicated publicly, but we want to reduce the exposure of in-group privacy as much as possible. You can think of it sort of like a membership card that authorizes you to different actions within the system, but doesn't reveal your identity in the process. Second proof we have is that the receiver agrees to the transfer. This ensures that we're not just allowing tokens to be sent to unsuspecting individuals. This is very important for the system to work properly. And it also validates that the new commitment that's being set in a transaction is appropriate to the receiver. Last proof we have is that the sender authorizes the transfer. This that they authorize the transfer is kind of like working through the nullifier in the Zcash protocol. It unlocks the old commitment, also demonstrating ownership of the token, and transfers it to the receiver in kind of one action. So here's a bit of an architectural drawing of the proof system, which shows the public and private parameters involved in the transaction, including what the sender, the receiver, and the network all know. And of course, the transaction is only valid if and only if all the private information is consistent with the public information of the transaction. So we need to make sure that lack of knowledge of any of the private data should invalidate the entire transaction. But of course, engineering has trade-offs. So some of the challenges with the naive design that I showed in the previous slides is that, well, first off, we wanted to ensure that a physical transaction between 2 participants is about on par with filling out the paperwork in a traditional transaction. So it should take somewhere on the order of 3 minutes to do. However, the unoptimized version of our membership authorization proof took about 45 minutes to generate. Obviously, we can optimize that down, but that's way too long, and it doesn't really seem possible that we're going to get both proofs and some of the other proofs all together to be underneath 3 minutes. So that's one problem that we had. And the second problem is that this is an interactive transaction. It requires both parties to run. However, both parties have personally identifiable information that they prefer to keep secret, and there's also private keys involved that control the secure the tokens that we don't want to have revealed even between the 2 parties. So we need a way to ensure that they can keep as much secret to themselves as possible. So our solution is to break up the proofs and try to get 2 birds with 1 stone. By breaking up the proofs in multiple components, we can prove them at different times by the different parties without exposing private information or taking too much time in the transaction. But this is tricky because when we do break up the proofs, we need to ensure that overall, in aggregate, they're showing the same thing, but we're not revealing or de-anonymizing anything in the process. We also need to ensure that the proofs are not replayable without secret knowledge, and that without, if you have one proof and you try to use it with a totally different thing, it shouldn't work unless all of them make sense together. This is especially important for authorization proofs because we're going to allow it to be used multiple times within a layer 2 sync cycle, which is about 1 week. So if you have a series of transactions, you don't have to recalculate the authorization proof multiple times. That's good news because now we can move some of this heavy computation outside of the physical exchange, meaning we have some faster UX in the process for the users when they actually go conduct the exchange. So here's a modified overview of the architectural drawing. You'll notice that all the public and private data is still the same between that and the previous one. However, now we have 4 proofs that are working together overall to show that the transaction is valid according to the same exact rules we had before. We solved this by adding some extra proof data that cross-links the proofs together in order to ensure that it's all internally consistent. So I'm going to go over some of the details how we did this. So for the authorization proof, we added an authorization view hash, which is a hash of the user's account, the authorization list, Merkle tree root hash, and a secret randomly generated number that both obscures the hash, demonstrates some secret knowledge for the other proofs. The randomly generated number is important because without it, it can do a pre-image tag, which is brute force iteration over all publicly known combinations in order to obtain what the hash is. The addition of the random number ensures that a brute force iteration isn't really feasible because now we have 2 to the 256 more potential combinations. So in the send and receive proofs, we added another special hash called commitment, which demonstrates the consent to the transfer of the token from both participants. So the send proof will resolve the commitment, very similar to signing a transaction in something like Zcash, and broadcasting that is making the transfer final and actually sets up the next commitment for the next transaction to occur. We're using a token view key in this commitment to show that both parties know the unencrypted serial number and that they consent to the physical transaction. It's sort of alluding to the fact, get out of here. It's sort of alluding to the fact that both parties know what the physical item is. So using the combo of the unencrypted, using this combination of the unencrypted serial number and the view key also acts as a additional mitigation against pre-image attacks, since the attacker would have to know 2 keys overall to defeat it. So in summary, went over some of the tips and tricks we used to help secure our protocol and improve the user experience overall. Some of the takeaways from this is that it's important to find the inefficient parts of the proof system and leverage some of the downtime inherent in the transaction in order to improve overall user experience. It's important to map the private and shared secret information together and to map that relationship of the secret data to the public data in order to ensure that the public data is necessary and sufficient for the proof system. Don't forget about pre-image attacks. They can be used to de-anonymize participants or allow unauthorized actions within the system. You can use random numbers as blinding factors in order to mitigate that. Splitting proofs can be really powerful. It can improve the user experience and allow better efficiency of the protocol overall, but it also increases complexity, and it could lead to a longer overall proving time since you have multiple proofs that you're now in aggregate doing together. But the good thing about that is you can do them more in parallel, or you can do them at different times, which is helpful. But you have to balance the potential performance gains with the added complexity. Otherwise, you run the risk of getting catastrophic bugs that could break the entire system. Also, don't forget that proofs can be reused. So you have to figure out a way that important actions can only be done once, or if you have a many-use proof like we do, ensure that that many-use proof can only be used in concert with a one-use proof in order to ensure that it can't be replayed. So that's all I had today. I'm happy to answer any questions about the tips and tricks I presented in the protocol. If you have comments or concerns about our proving system itself, you can come speak with me afterwards, and I'm happy to answer any questions. And of course, GitHub if you want more details. Thank you.
Hey, so I have a question that is a little bit general to supply chain applications, but then it seems like the privacy aspect makes it even more complex. So like what happens if a gun is stolen, or if another case would be a user's credentials are stolen? Without privacy, it seems like that could be reconciled by like patching up the ledger somehow after the fact.
Yep.
But with privacy, is there any,
So
have you
there's
thought
kind of
about those
two
challenges?
questions there, right? There's one if the firearm is stolen, is one
Right.
if you lose your wallet or phone or it's stolen and it's being used as you, basically.
Sure.
So I'll do the second one first. So what's really cool is that this is transacting a physical asset. So you're not going to lose access to the asset. You still have it at home if you just happen to lose your phone or whatever. So we can set up a new identity for you in the system, and that identity allows you to do the actions in a zero-knowledge way. Within the system, we'll just mint new tokens for you.
So wouldn't that end up with two different credentials controlling the same serial number in the system?
So the serial number in the system is an encrypted serial number, so it's the raw serial number and like a secret random nonce that encrypts it. So they'll just generate a new secret random nonce, and it won't be the same number. However, the underlying serial number is now shared between two tokens, which is bad. So when we do reissue that, it'll be recognized as a duplicate, and we'll be able to say if no one responds to this in a month, then it's fine, right? We can delete the old one and add a new one.
Okay. And how about the other case?
So the other case was if the firearm is stolen, right? Mm-hmm. So you still have access to the keys on your phone or wallet, and you can use that information to reveal to law enforcement, the general public, whatever you want to do, because it's your information, that did occur, and that actually aids law enforcement in tracking down what's happening. And you don't ever have to talk to them because it's on your phone. You can just like release it.
Okay. Actually, there's a third edge case I was wondering about. So what if you are law enforcement or anyone else and you find a firearm and say everyone is using GunClear, so everyone knows it's a GunClear, it's tracked by GunClear. They find the firearm. Is there any way to figure out which credentials it's associated with? Like what would be the recovery?
So there's no way to actually figure out from like all the encrypted information, but you do have like a kind of hot potato case, so you know where it starts, right? Or if it starts from a manufacturer, you just go ahead and ask the manufacturer. There's obviously connections there between law enforcement and the manufacturer, or even a resale store. You can start traversing that chain of ownership and asking each individual, like, who'd you give it to, who'd you give it to? And you have, it's like playing a game of hot potato. At some point, you either can't give it up because you don't have somebody you gave it to, and you can't prove that you did so, or like, it kind of ends and it goes back into the traditional system somehow, or, it gives a bit of a vector into attacking that problem without revealing everyone's information publicly.
Thanks.
Sure.
So at least the basic protocol, without the proof splitting, it seemed to me as though ZEXC would be expressive enough to represent that protocol. Am I correct about that? Or
I haven't looked into it too much, but obviously there's a lot of things we can do to optimize this, and there's a lot of other alternative systems we can use to do this. So it's all active research on our part. I just wanted to go through like the very naive version of what we did and to share some of those learnings.
So in terms of anonymity set, if you're sharing the anonymity set with another payment or computation protocol, that's obviously going to be much larger.
Yes, yeah.
So the other thing that occurred to me is that the proof splitting was a little bit similar to the splitting of spend authorization in Sapling. Okay. Did you consider using that technique where you're just using a signature for authorization?
Yeah, I actually thought about that because, like, at the end of the day, this is like a layer 2 to Ethereum system, and like we're using the account codes, the account addresses, in order to like represent the individual. So we could have them just sign things basically in order to do that. It would be interesting. obviously more things for me to explore. There's a lot to explore.
Okay, thanks.
Thank you.
Hey, in one of the early slides, I think you had a note that the send proof acts as a, this is like the third slide or something, when you were laying out the initial proof structure, the send proof acts as a two-factor authentication for the physical firearm. I was just wondering if you could explain what you meant by that.
Which slide again?
Keep going back.
I think I went back too far.
Okay. You had the structure of the proofs, the initial one, that one right there.
This
back.
one, okay.
Yep. Number 3.
Yeah.
The second bullet point.
Yeah, so you have the physical, firearm itself. That's obviously what we have today. People pass it around. There's some paperwork sometimes that happens. Here we're actually creating like a digital piece of paperwork that's following around the firearm like in parallel to it. So when you're passing both pieces of information along at the same time, it's kind of acting as two factors. So you have the physical device and the digital representation of it. And that means like in a given transaction, if you can't show that you have the token and pass it along, or you don't have the physical firearm, then there's like a break there. So like they both have to move together for it to be, logically consistent. So that's the analogy I'm drawing, yeah.
Cool, that's really interesting, thanks.
Thank you. Gave a lot of time for questions.
Yeah, I was curious if you could just describe the implementation of the zero-knowledge proving, like which libraries you use, or how are the circuits?
So my partner on the project is actually doing like the low-level stuff. I just helped design the proof system because I'm kind of architecting the whole thing. But we're using Libstark, and he helped. I think he created a KECAC 256 thing and something for ZKP 256K1. I don't know if those existed before.